I'm Mihai Maruseac from Google Open Source Security team, where I'm working on AI and supply chain security. And I'm going to talk about taming the Wild West of ML, basically model signing and supply chain security for ML. And I couldn't start a presentation about supply chain without the classical XKCD diagram. We have seen a lot of AI talks with a lot of AI products with a lot of nice things about AI. But there is still that little piece in there which stems from the AI supply chain security. And over this presentation, I'm going to wear different hats as a model trainer, as a model user, and as a model attacker to actually show you the problem and the solution. And let's directly switch into a demo. So I am going to act right now as a trainer, and I am going to train, let me connect. I am going to train a simple model using the MNIST dataset once I can connect. And then I'm going to act as a user using that model. OK, so let's train the model first. Train. It's the simplest TensorFlow model. MNIST is the tutorial example. I didn't want to go too deep into this part because we are not interested in that. It's going to take a few seconds. Then I'm going to upload this model to a model hub where I have access, where I can actually act as an attacker. And then as a user from a separate machine, I'm going to download the model from there and try to use it. So one more iteration. And we have this demo model.keras, which I'm going to upload to the model hub. And now let's switch to the user. So as the user, right now, I only have two scripts. One is to use the model. The other one is to download the model from the model hub. Let's download it. And that was called demo model.keras, which I now have here, and I can use it. And it should give me a prediction for a specific image that contains a digit. It is the digit number 8. That's what is shown in the diagram in the outputs there. OK, so now let me put on the attacker hat. You see the background is red. I am on the model hub. I have the model in here. But I also have a stashed script that is going to hack into the model. So now if I'm going to hack the model, I basically load the model inside TensorFlow. I maliciously alter it. And then I save it again. And now let's switch back to the user. Let's delete the old model and download it again. Suppose now that the user doesn't know that the model has been tampered with. Sorry. Python download demo model. And then trying to use this model. This time, TensorFlow starts loading, starts to load the model, and then you have been pwned, and then some error. So right now, because the user didn't know that the model has been maliciously altered, their system could have been taken over. And this is not a fault in just TensorFlow. PyTorch has the same issues. Basically, every model has a serialization format issue. It could also happen with architectural backdoors, where a specific input phrase in an LLM, for example, could make the LLM behave totally different than expected. OK, so how are you going to solve this? This is not a problem that shows up in just one single scenario. In general, in industry, you have multiple stages for an LLM to train. You have big companies that are training foundational models on the entirety of the internet, and then other companies are fine-tuning this model and then deploying it into an application. So you have at least 3 separate teams. And in between the teams, the model goes into storage, either internal storage or public storage like Kaggle, Hugging Face, and so on. And in all of these places, you could have possibilities for alterations of the model. And it's not just something theoretical. There was actually an incident at the end of last year where a TikTok intern was sabotaging another one, sabotaging the training run after maliciously altering a checkpoint, such that the other intern then would start training a model from a malicious checkpoint and generating a bad model out at the end. OK, so now let's switch perspective a little. Let me put on the attacker hat again. And let's say I want to compromise some users. and I want to compromise the users using ML. I trained 2 LLM models. One is called Evil model. I basically train it on 4chan. And the other one, sorry, one is Evil model, has malware in it. And the other one, GPT-4chan, trained on 4chan. I have to put the models on some model hub such that the users will then download the model. Of course, on the model hub, I put some nice descriptions for the model. So I say that the first one helps you detect the malware. And the second one is a friendly chatbot for some definition of friendly. At this point, the users are still not going to download the models because the name of the model doesn't sound like something that they would want to do. But that's easy to fix. I can just change the name of the model. And again, this is not something theoretical. We have here 2 models on Hugging Face. One is from Meta Llama, and the other one is from Facebook Llama. And both of them are Llama 8B. Only one of them is real. The other one is actually a researcher trying to prove that this is actually something real that could happen. And when you look at the statistics, at the stats on the model, you can detect which one is the right one. But imagine a new model gets released, and then at the same time, attackers are also releasing typo-squatted versions of that model. And now the number of stars and the number of users are going to increase almost in parallel. It will be hard to look at the statistics to know which one is the legitimate model. Okay, so finally, let's look at the diagram on how a model gets trained. We start with data sets, which we collect from the internet or internally, and we iterate on them. Then we select an ML framework like TensorFlow, PyTorch, JAX, and so on. We define the architecture of the model, and we run a training script to train this model. Once the model is trained, the model gets put to a model hub, and from there it can either go back into more rounds of training, so fine-tuning or assemble models and so on, or it can be elevated to a production model where it's being given on to some other team to deploy it into an application. And at every step into this process, we have supply chain security risks. So for data sets, you can have data poisoning. You can get data already invalid from the internet, or while doing data cleaning, somebody malicious might ingest malicious data inside the data set. You have model poisoning, as the demo that I was showing you, injecting malware inside the model. We can trick users to use the bad model. That was the scenario with the 2 Hugging Face models, 2 Llama models on Hugging Face. And there are also other vulnerabilities in other places. So this is what we are trying to solve. And the first step in doing this is to establish trust by model signing, where we want to sign the model as soon as it gets signed. As soon as it gets trained, we want to sign it. And then each time the model gets used, we want to verify the signature. And if I switch back to the demo, and I can show that. So let me switch back to the trainer. Actually, let me switch back first to show you. This is the repository that I'm going to talk about. It's called Sigstore Model Transparency. And from the repository itself, it can be run with hrun, Python-C model signing. Python-M. Or it can be run as a Docker container, actually contributed from people from Red Hat. Or once you install it as a Python package, you can run it with Python-M model signing, or directly as a binary. So once you install it, you have 4 different ways to run it, depending on your use case, depending on your scenario. And there is future work to actually start supporting a C++ version, a Golang version of this, such that you don't have to install a Python system just for signing and verifying models. OK, and the tool supports signing and verification for models. So let's do sign. And again, the help screen is telling us that it can support signing with certificates, with keys, or with Sigstore. I'm going to talk about Sigstore in a short while. But now for this demo, let's do signing with keys. So I'm going to use OpenSSL to generate a key, a private key, and then generate the public key that corresponds to this pair. And then I'm going to sign this model sign with the key. And just to show the help screen, I have to pass the path to the private key. And then the path to the model. The model was demo model.keras. And signing succeeded. Ignore the log screen, the log messages. And I have this model.sig. This is the signature. And now I can just upload both of them to the hub. So let's do upload demo model and then model sig. And now as the user, I am going to download demo model. And I'm going to download the signature. And now I can verify this, model signing, verify key. And let's do some help screen because I always forget the arguments. We have the public key. Oh, I forgot to update the key to the server, so let me do that too. I have to upload the public key here. And as the user, I also have to download it. Key.pub. Okay, so model signing, verify key, public key, that was key.pub, the signature, model.sig, and then the path to the model, that was the demo model. And this time, the verification succeeded. If I try to do the malicious attack again on the hub, this time it will fail, because the hub cannot sign the model. Okay, so let me go back to the presentation. And we have two main questions now. What is different in model signing compared to signing just a simple file, just binary signing? And what is different compared to signing a container, which is like a set of layers? So for models, we have four different criteria here. The first one is atomicity. Models in general are multiple files, a collection of multiple files. Right now for Keras, it was just a single archive. But if I go back to the trainer, I have other models in here, like I have BERT, which is a very large directory with a large set of models. So models in general are multiple files, and a model is valid if you have all of the files together, not tampered with, and exactly with their name. So an attacker could, for example, to cause a denial of service for one model, could interchange the name of two model files. File A is now going to be file B, and file B is going to be file A. And the model now cannot load, but if you sign it as sign every file individually, all the signs, all the hashes will still match, because I only changed the names. Moving on, the next criteria is the size. Models in general are of various sizes. So we could have models several kilobytes, several gigabytes for very small models, up to terabytes. On this directory here for the trainer, if I do a demo, BERT is 6 gigabytes, and this other small model here is 2 megabytes. So these are like two extremes that I use, and we can sign both of them in kind of a similar time. The problem with the size is that in order to sign, you have to hash every bit of the model on disk, and now you are depending on the disk performance. So very large models will take a long amount of time to sign. And now you get into the next problem about serialization, where ideally you would want to sign both the end model, so the result of the training, but also every checkpoint that gets generated during training. Because you could go back into the Baidu scenario where the training takes a long amount of time, somebody tampers with a checkpoint that just got saved on the disk and then causes the training job to crash. And now when you restart, you are restarting from a checkpoint that has been altered. So ideally you would want to hash everything that gets generated during the training job. The problem is that because the sizes are big, you cannot wait a long amount of time to hash while the CPU resources, the GPU resources during training are not in use. So we have to make hashing efficient. Then there are also multiple formats for models. So we have the Keras model that is just one file. We have safe tensors that is a collection of files. We have GGUF, which is another set of files, and so on. And on some repositories, like on Hugging Face, you could have all of these files together into a single name. So if I switch back to this BERT model example, I see in it I have a PyTorch model as just one single file. I have one file for safe tensors, one file for ONNX, and I have a collection of files for CoreML. And all of them are in the same repository. As a user of this model, I only care about one specific format. When I verify the integrity of a model, I shouldn't need to spend time to hash everything that is in the model directory. I should only verify the hash of what I am using. So for verification, we need to take into account that the framework that the user is using. Okay, and finally, on the user side, there is also the cases of distributed training and distributed inference, where you have multiple hosts writing to the same model at the same time. Ideally, you wouldn't want the controller of the distributed job to do the hashing for signing or verification. You would want each individual host to sign or verify the pieces that they write or read. And of course, there are a lot of ML frameworks, a lot of hubs, a lot of pipelines. Ideally, we want to integrate into everything to work everywhere. Okay, so now let me go to the Sigstore part. So far, I have signed with a key. And as the user, when you wanted to verify, you also needed the key. And in order to pass the key from the trainer to the user, I had to put the key into the model hub. There is nobody stopping the model hub malicious insider to actually generate a private key inside the hub, sign the tampered model, and then say that this private key that they generated is the one that people should use to verify the models. With Sigstore, I can do something else. Sigstore tries to elevate this problem, so key leakage, material secret leakage. So what Sigstore does, let me go back to the diagram. As the model trainer, either as the human or as the pipeline, you connect to the Sigstore certificate authority and get a certificate that is valid for a very short amount of time, like 10 minutes or something like that. Very similar to how Let's Encrypt works for HTTPS certificates. You get a certificate that is valid for 6 months, and after that, you have to keep renewing. Once the model trainer gets the certificate, it signs the model and then passes the signed model and the certificate to a transparency log, which can be inspected such that people can see who signed the models in their name, when was the model signed, and so on. And you get back a log inclusion proof, which is then included into the signature. And now you upload to the model hub, you upload the model, the certificate, and the proof as the signature, as one single bundle. The model hub can now verify the signature and display a nice badge, this model has been verified. And then the users, if they trust the model hub, can just download the model and use it. If they don't trust the model hub, they can run the verification themselves. That is the scenario that we want to do. And now let me do a demo first on signing. So I'm as the trainer, model signing, sign, and I'm going to sign again the demo model. Okay, so it's hashing the model, and because I'm a human and not a workload identity, I have to first log in with some OIDC provider. So I have this link here, where if I click on it, it should open a browser tab to log into Sigstore with some OIDC providers. In this case, I could choose GitHub, Google, or Microsoft. Other services could provide more. So let's say I'm picking GitHub, and I copy this code, I copy it back here. At this moment, Sigstore CA is generating for me a certificate that is valid 10 minutes, which I can use to sign once. Once I press enter, that is going to be used, sign the model. Everything is going to be put into the transparency log, and the signature is going to be generated here. So now I can look into the model sig, the signature. This is a JSON file, so let's also pass it via JQ. And there is a payload that contains everything that I have signed over. But what is relevant for Sigstore is actually the part above, about the inclusion proof that tells me that this has been included into the transparency log. And the log index, which tells me exactly where I've been integrated into Sigstore. And I can take, for example, this log index and go to Sigstore and search here for that log index. And I could see the signing event into the transparency log. I will see the short signed certificate, which is valid from 1 minute ago, and it's still valid for 9 more minutes, but you cannot sign anymore with it. Sigstore is going to deny it. And I can see every other field in the certificate. I can see the raw body of the certificate, and I can see the verification, the inclusion proof, which I can match with the signature if I really am paranoid. So I can match any of these hashes in here with any of the hashes included into the signature. Okay. And then the verification could do the same. Let me switch back to the slides. OK, basically the signature is a bundle that contains a hash for every file into the model, and the signature with the inclusion proof as I've shown you. And our project so far, released on GitHub, has 160 stars, a lot of downstream users, and we are collaborating on it under OpenSSF, Open Source Security Foundation, and Coalition for Secure AI. OpenSSF has a model signing working group where people can collaborate on this, and then Coalition for Secure AI is more working towards standardization and extensions of the signature. And for us, speaking of the future, we want first to have green check marks across the entire supply chain. So sign datasets, sign models, verify everything when you use it, sign TensorFlow, sign every binary, and verify it before you use it. And we also want to go above signing. So we want to generate salsa provenances, we want to generate S-bombs, and so on. Basically, we have like 4 directions to go here. For future of signing, we want to do, as I said, signing to datasets. We want to integrate with model hubs, model frameworks. We also want to integrate with agents. So when you have one LLM talk to another agent, maybe if that agent is somewhere else remotely, they should authenticate, they should be signed, the agent card should be signed. That's something that we are actively working on right now. Then moving on to more supply chain transparency, we want Salsa for ML. So record that this model has been generated from this dataset at this specific version of TensorFlow on this specific builder, such that you can build lineage transparently and automatically. You can go directly from one model used in production to the dataset that has been used to train it. And at some point, we might want to go to an ML package manager. So similar to how you do DNF install some package, you could do, let's say, ML install a dataset or ML install a model. And behind the scene, this will make sure that the integrity of what you are installing is correct. We'll make sure that if you use it to train another model, that is going to be tracked. And the idea is to generate tamper-proof ML metadata, such as model cards, model evaluations, and so on, to be able to also generate AI bombs automatically. So rather than you scanning the model once it has been generated and then generating the AI bomb, everything will be generated automatically for you. Basically, we want all the claims in ML to be tamper-proof and tied to some identity. And at the end, you can build a telescope that you can inspect. Given from a model, you can detect exactly what has been used to generate the model, what data set, what pre-trained model, and so on. All of this vision has been in a white paper that we published almost a year and a half ago. And the latest update has been from somebody from Red Hat. They provided a Docker container, a big project on Sigstore, model validation controller, which allows you to verify a model, to verify the model signature and everything without you having to download the model locally and install the entire set of packages and then use it there. I'm going to leave some links here at the end of the slide. The slides are already published on the schedule. But before finishing, I'm going to also show you 2 demos where the model signing is already integrated. So we have the NVIDIA NGC, the NVIDIA Model Hub, where they have a bunch of signed models, which are already signed, and users can download the model, can download the signature, and can verify them. And then on Kaggle, actually on Kaggle, I have to upload the model. So let me do Python upload small model, Kaggle. And while this is uploaded on Kaggle, you could also see the verified badge. So Kaggle is signing the model locally using a workflow identity and a Kaggle OIDC. And it's uploading everything to Kaggle. So you'll have this signing.json. This is the signature that Kaggle generated. And if I go to this link, this is the model uploaded on Kaggle. And right now, if you look here on Sigstore status, it says pending. This is when Kaggle is actually verifying the signature. I showed everything into a single step, but actually you would sign the model locally, and then you upload the signed model separately. So that's why the verification has to be here. One more second. OK, so now this is signed. If I click on attestation, I can see exactly how I can prove this. But I can also see the signature here under Kaggle. Signing JSON is exactly the signature. And if I copy, let's say I copy the payload, and I inspect it. So let's say echo the payload, base64 decode, and then this is the JSON. This will tell me the hashes of every file into the model. So if you want to inspect manually, if you don't trust the tooling that verifies the signature, you can also inspect manually. And everything that was there should also be in Sigstore. And now I'm going to stop for questions. Yes. So the question was about integrating containers, integrating the model signing into pipelines, so like Llama and so on. Yes, ideally we'd want to integrate both with the framework itself. So like when you say model.save in Keras, behind the scene this will sign the model for you. When you say model.load, it will verify the signature. On the container itself, on the platform, it could also verify behind the scenes. So the end goal is to have like everything signed as soon as it gets generated, verified just before use. Lunchtime.